In previous lecture, I was talking about one-dimensional discrete models, discrete systems. So they described by so-called difference equations. And in case of example 1, which we considered last time, it was looking like this: un plus 1 equals to, I will put it like this, AUN plus B. So this was our example we considered on lecture 2. And this is difference equation, and this difference equation is so-called linear difference equation. In fact, it's linear difference equation with constant factors a and b. So more general way, general linear equation sounds like this: un plus 1 equals to a as a function of n times un plus b as a function of n. So this is still linear. Now, let's put it like this. Generally, first order, let's say first order difference equation is, like, we can put it like this: un plus 1, some function of un and n. And so this is first order general. And if un plus 1 equals to f of un, so it's not explicitly depends on n, this is called autonomous. Autonomous first order differential equation. Now, as next, we can put, so un plus 1 can depend not only on un, but on value of u in previous time step, previous, before previous, and n. So this is second order difference equation. And I will illustrate it using second example. Second example in lecture notes, it's on page 4, which is called Fibonacci model. So this Fibonacci model, it was designed long time ago. I think it was like 13th century, maybe 14th, maybe even earlier. And it was modeling growing population of rabbits. So model assumptions. So we consider growing population of rabbits, and first assumption is like this: rabbits bring the offspring once per year. It can be reformulated, but let's leave it like this: bring the offspring once per year. Second assumption, that size of offspring. Size of offspring one pair of rabbits. One rabbits. And third assumption, rabbits live 2 years. So I corrected my mistake. Now, so we have this model, and this model describes dynamical system. In this dynamical system, quantity describing this dynamical system, let's call it U again. U is size of population. Number of pairs of rabbits, we can put it like this. Then assume in year one, initially, is year 0. We have certain number of pair of rabbits, and they all young, yeah. So U equals to U naught, and they all 1 year old, 0 year old. Zero years old, all of them. Then first year, we will have number of pairs of rabbits is U1, and this will be equal to U naught, which are now 1 year old. I will just call them old. It is same as we had in year 0, but each of them gave rise to extra pair of rabbits. So they gave offspring. Therefore, this plus U naught times young. I call them young in my lecture notes. So this is 1 year old. And this is 0 year old. So in the second year, since rabbits live only 2 years, this died out. This will become young, will become old. But in addition, both of them give offspring. So this will be plus U1 young. And if we now consider third year, it will be same story. Those which are old will die out. This will become old, U1 old, and both of them, U naught and U1 old and young, will give birth to offspring, and therefore it will be U2, and all offspring is young. And therefore, we can conclude, now you see what happens. U2 equals to U naught plus U1, U3 equals to U1 plus U2, and we can prove it, but more formally, but it's more or less evident. So UN plus 1 equals to UN plus UN minus 1. So this is second order difference equation. Now, our problem is to find un is kind of function. I don't know how to put it. Let's say f of u naught and eventually u1. So this would be solution, analytic solution. So why it should depend on u naught in addition to u1? Because this equation can be used to find u2, but it can't be used to find u naught and u1. So therefore, u naught and u1 should be given. U naught, u1 form initial conditions for this problem. And so I will give you heuristic way to explain how to solve these kind of equations. So just referring to first order difference equation, you remember that if you, well, let's keep this x n plus 1 equals to a times xn, then we know that xn solution is a to the power of n times x naught. And for second order difference equation, linear difference equation, like xn plus 1 equals to a1 xn plus a2 xn minus 1, we still can try to find solution in similar way, but we don't know what to use instead of a, and we will use lambda to the power of n times x naught. And further on, we can say if x naught equals to 1, then xn can be looked as lambda to the power of n, for example. Yeah, and this is what we will do in terms of our difference equation. This difference equation, un plus 1 equals to un plus un minus 1. Let us try un equal to lambda to the power of n. So if this kind of solutions exist, then we can find lambda. So if this is a solution, then if we put it back to this equation, that what we will have, lambda to the power of n plus 1 equals to lambda to the power of n plus lambda to the power of n minus 1. If we divide all of this equation by lambda to lambda minus n, it will be lambda squared equals to lambda plus 1, or lambda squared minus lambda minus 1 equal to 0. So roots of this equation, it's quadratic equation, lambda 1, 2 equals to 1 plus minus square root of 5 over 2. So we have two roots, and generally un could be equal to lambda 1 to the power of n. It satisfies our equation, and un also could be lambda 2 to the power of n, and it also satisfies equation. Furthermore, un equal to some constant c, say c1 times lambda 1 to the power of n, also satisfies also solution, and un equal to c2 to lambda 2 to the power of n is also solution. And at the end, last point is, so linear combination of solutions is also solution. Therefore, n equal to c1 lambda 1 to the power of n plus c2 lambda 2 to the power of n is solution, general solution. I will call it general solution. To this difference equation, to un plus 1 equal to minus 1. You can check it. We can, if you put this, so it is easy to check. It will be identity where, okay, I put it where lambda 1, 2. Now I give before these two. This can be easily checked. We put this into original equation. Un plus 1 equals to un plus un minus 1. And this means that un plus 1 will be c1 lambda 1 to the power of n plus 1 plus c2 lambda 2 to the power of n plus 1. And this should be equal to this is this. Un will be c1 lambda 1 to the power of n plus c2 lambda 2 to the power of n. This is un, and finally un minus 1 we will replace by c1 lambda 1 to the power of n minus 1 plus c2 lambda 2 to the power of n minus 1. So you can check it, its identity. Therefore, we found analytic solution for this. And last thing to mention, C1 and C2 are found from U0 and U1 from initial conditions. Now, next observation about this. So UN is C1 1 plus square root of 5 over 2 n, it's lambda 1, C2 1 minus square root of 5 over 2. So what is important? This 1 plus square root of 5 over 2 more than 1 minus square root of 5 over 2 by absolute value is less than 1. And therefore, this tends to 0 as n tends to infinity. So in the long run, un tends to c1 1 plus square root of 5 over 2 to the power of n, when n tends to infinity. So this is one observation. And second observation is about ratio of un plus 1 to un. So let's put it like this: limit of un plus 1 to un when n tends to infinity. This will be equal to c1 1 plus square root of 5 over 2 to the power of n plus 1 over c1 1 plus square root of 5 over 2 to the power of n, and this equals to 1 plus square root of 5 over 2. So this limit is called golden ratio. It is very famous number describing Fibonacci sequence, so-called Fibonacci sequence. And last probably thing what to do is to tell you about Fibonacci sequence. So Fibonacci sequence is sequence of these numbers. It is so 0, 1, 1. So 0 and 1, it's two original numbers, and 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and then 8, and so on. So here, this is U0, this is U1, this is U2, U3, U4, U5, and we know that UN equals UN plus 1 equals to UN plus UN minus 1. So this is our sequence. The only interesting story about this is whether you can find, so what we have u naught equals to 1, to 0, let's say, u1 equals to 1. And we know that un equals to c1 lambda 1 to the power of n plus c2 lambda 2 to the power of n. Lambda 1 and lambda 2 was already found. Can you find for this problem? Find c1 and c2. So this is, I think I have it in my lecture notes, but it would be good if you practice this. Now a bit of theory about fixed points and their stability. So I will get back to this simple example we had, to geometric progression, xn plus 1 equals to axn. So we know for this that solution is xn is a to the power of n x naught, and we know that xn tends to 0 if a by absolute value less than 1, and say xn diverges if a by absolute value is more than 1. On the other hand, what we can say, x equal to 0 is fixed point. We discussed it, is fixed point, which means that if x naught equals to 0, then xn equals to 0 for any n. So it's fixed point. And another observation, what we see, if a by absolute value less than 1, then xn tends to fixed point. So this is my main point here, fixed point. So fixed point is known solution, stationary solution, and there are two classes of fixed points, such fixed points to which other solutions converge, like in this case, or fixed points to which other solutions do not converge, like in this case. And these two cases correspond to two different classes of fixed points. So let's formulate it. We consider a map. Let's consider autonomous map for now. Well, we will consider autonomous maps mostly in this course. So first order autonomous map. Now, assume U capital is fixed point. We know what is how to find fixed points. U is root, one of roots, or maybe the only root of this equation, algebraic equation U equals to f of U. Now, U is called U capital is asymptotically stable. If there exists some neighborhood delta of U capital such that if U naught minus U capital by absolute value less than delta, so which means that U naught is in delta neighborhood of U capital, then UN tends to U as n tends to infinity. So in this case, U capital is called asymptotically stable. This means that if U naught is some neighbor, there is a neighborhood of U capital such that U naught inside of this neighborhood, then our solution will converge to U capital. If instead of convergence we have this condition, U n minus U capital less than epsilon, kind of epsilon, there is epsilon such that U n minus U capital, or we can put it like this. If for any epsilon we can find delta, it sounds like this. Okay, I will reformulate it. I will remove that and formulate neutrally stable condition. U is only stable or neutrally stable if for any epsilon there is delta such that if U naught minus U capital by absolute value less than delta, then Un minus U capital by absolute value less than epsilon for any n. So this is neutral stability. And now I can state a theorem which sounds like this. Fixed point U capital of the map Un plus 1 equals to f of Un is asymptotically stable if derivative of f of U when U equals to U capital by absolute value less than 1. So this is a statement, and it is proof is very simple. Oh, this statement is very strong, very, very important, and proof is relatively simple. So we have Un plus 1 equals to f of Un. Let's consider Un, which is U capital plus, so not far from U capital, something like epsilon. So difference, or I can put it different way. Let's put it different way. I will introduce, I will make substitution. Substitution. Epsilon n equals to Un minus U capital. And assume epsilon n, oh yeah, much smaller than 1. It's very small. Then we can rewrite our equation this way. So this will be epsilon n plus 1 plus U capital. So this is Un plus 1, and this will be equal to f of epsilon U capital plus epsilon. Yeah, so this is Un. And this will be equal to, now what we will do, we will take Taylor expansion of this f. This f of U plus derivative of f at u times epsilon n. So I will say here roughly equal, because it's approximation. And what we know, this equals to u capital. Therefore, this cancels this. And what we got difference equation for epsilon times epsilon n. And for this, we know solution. Epsilon n is this derivative to the power of n times epsilon naught. We had it before, and we know that epsilon n tends to 0 if this number by absolute value less than 1. It is also discussed before. This completes our proof. If we consider this map, now let's point out to this f of un, and u capital is stable, let's say stable fixed point. It means that there are some set of u nodes that exist. U nodes such that un tends to u capital, and all set of these u nodes form something which is called basin of attraction of u capital. Okay, I will stop here.